Okay, so this week our lab is going to be over heat transfer and change of phase. So, two different concepts, but two concepts that are very closely related to each other, which is why we have them in the same lab here. So, the very first part of the lab is going to be over heat transfer. And what we mean by heat transfer is any energy that it's exchanged between two objects whenever there's a difference in temperature. So if I bring, for instance, in this lab, we're going to be bringing a hot piece of metal into contact with water, and the metal will be at a greater temperature than the water will be. So that means that the heat will be transferred from the metal to the water due to this difference in temperature. Okay, and then heat is always transferred from hot objects to cold objects. Okay, and this is due to the fact that they want to be in equilibrium. So whenever you bring two objects into contact, they want to exchange heat until they are the same temperature, and then once they're the same temperature, heat is no longer exchanged. Okay, now the equation for heat is the following. So we have H, which stands for heat, is equal to the mass of the object, all right, times the specific heat, C, that we'll talk about here in a second, times, again, this very important change in temperature, delta T. So this delta, this triangle, just means change in temperature. Okay, so another way of writing this would be MC, and instead of delta T, we can say the final temperature minus the initial temperature. So you can see if there's no change in temperature, if my final temperature is the same as the initial temperature, then the heat will be zero. Okay. Now, mass, I think, is easy enough for you to understand. It's just the mass of the object that is being that heat is either being transferred from or to. All right. But specific heat might be a new concept to you. And so what specific heat is, it's the amount of energy that an object can store per degree Celsius, per unit of mass. Okay. So water, for instance, can hold 1 calorie per gram degrees Celsius. Okay, so for every temperature, for every degree that our water changes, for every gram of material that we have, to get 1 degree Celsius of change, we have to add in 1 calorie of energy. All right, so the higher the specific heat, the more energy I have to add to a substance in order to raise 1 unit of mass 1 degree Celsius. That means that it can also hold a lot more energy, so it loses its energy a lot slower than, say, metals, which typically have a really small specific heat. This is why metals are very good conductors of heat, is because it doesn't take much energy in order to raise their temperature 1 degree. Right? Whereas water is a good insulator of heat. It holds a lot of energy. It takes a long time, as we all know, to boil a pot of water. Right? Your pot that the water is in will heat up much quicker than the water does, and that's because of its specific heat. Okay, so now let's talk about heat transfer. Anytime two objects are brought into contact, right, we already talked about there's going to be an exchange of heat between the two because of the change in temperature, but this exchange of heat has to obey the conservation of energy. So that means, if we write this down, that the negative heat lost by one object has to be equal to the heat gained by the other. So in our case, for the metal that we're going to be, for the hot metal that we're placing in water, we're going to say that the negative heat lost of the metal has to be equal to the heat gained by the water. All right, and now if we write this conservation of energy in terms of this equation that we have for heat, right? On the left-hand side, we would have negative mass of the metal times the specific heat of our metal times the change in temperature of our metal. So the final temperature for the water and for the metal are going to be the same, so we'll just write final temperature, but they will have different initial temperatures, so we have to make sure that we mark this as the initial temperature of the metal. Okay, so that's the left-hand side here. This is going to be the equation for the heat lost by the metal. And on the other side, we're going to have the heat gained by the water. So we're going to have the mass of water times the specific heat of the water and then times the change in temperature of the water. So again, our T final for the water and for the metal are going to be the same, because that's going to be whenever they've come into equilibrium. And then we're going to subtract the initial temperature of the water, which will just be room temperature. Okay, so we're going to heat up our metal and then place it into some room temperature water. And then this is the equation for the conservation of energy between the two objects that we're going to put together. Okay, and now the goal of this lab is going to be to determine what is the specific heat of the particular metal that we're using. Okay, so we're going to be using aluminum and copper as our two different types of metal. All right, and we have the accepted value for the specific heat of those. And now we're going to use this equation to then calculate the specific heat of that metal and compare it to the values that are given to us. So that means that we need to solve this equation in terms of the specific heat of the metal. So we want to get everything on the right hand side except for the specific heat. Okay, so let's do that. So we're just going to do some algebra here. So let's first distribute this negative sign into this difference between our two temperatures. So if this negative is distributed, that would make our final temperature negative, and that will make our initial temperature positive. So another way of if we rewrite this, after distributing that negative sign, we just flip the order of what's inside of our parentheses. So it's going to be the initial temperature instead of the final temperature minus now the final temperature. Okay, so all we did was distribute that negative. We're going to keep the right-hand side the same. All right, and now to get Cm by itself, I have to divide both sides by the mass of the metal, and I have to divide both sides by this difference in temperature here, and that would give us this specific heat of the metal by itself. So let's do that. So if we say, that would leave us with our final equation for the specific heat of the metal. Times the change in temperature of the water. All right, divided by now, right? We divided both sides by the mass of the metal and by the change in temperature of the metal. Okay, and then this is the final equation that you're going to use. This is the equation that you'll see in your manual. And that's what we're going to use. So you can see that we need to know a few things in order to find out what is the initial temperature, or what is the specific heat of our metal. We need to know what is the mass of the water that we're adding our metal to. We need to know what the specific heat of the water is. It turns out the specific heat of water is 1, so we can actually ignore that, because 1 times any number is just the same number over again. So we don't even have to worry about that term, okay? Then we need to know what is our final temperature, what was of the metal of the water and the metal after they've been added together and they've reached equilibrium. What is the initial temperature of the water? What is the mass of the metal that we're adding to the water? And then again, what is the initial temperature of our metal and again the final temperature? So we need to know quite a few things in order to calculate this specific heat. And so that's what this lab is going to be doing, is you're going to first be measuring all of these things, and then we're going to heat up our metal by placing it into boiling water, and then we're just going to add that metal to our water and then wait for them to come to equilibrium so we can get this final temperature. And then you just plug all of the numbers that you have into this equation, and then you'll get an experimental value for the specific heat. All right, and that basically is the entire first part of the lab involving heat transfer. Now, the second part of the lab also involves heat transfer, but it's what happens whenever I add heat to an object, but the temperature just doesn't change. Okay, and the temperature isn't changing because it's undergoing what we call a change of phase. Right, so we have 3 main types of phases. You have a liquid, solid, and a gas. And anytime an object is going from one phase to another, its temperature is actually going to remain constant, even though we're adding heat to the system. And what we call this added heat that doesn't change the temperature, we call it latent heat, or you can think of it as hidden heat, because it's not immediately apparent where this heat is going. Let's make sure that we're separating these two because they are sort of different parts of the lab. So we have LV is the latent heat of vaporization, and this is the heat that we add whenever we're changing a liquid to a gas. All right, so we're changing a liquid to a gas. It's undergoing a change of phase. The heat that we're adding, instead of going into changing the temperature, is actually going to go into moving around the molecules. So changing the position of the molecules within the substance. Okay, and that's why it doesn't change the temperature, is because it's changing the actual structure of the material. So that's for vaporization. There's the same equation we can use, but this time it's going to be the latent heat of fusion. And what this is the amount of heat that we add whenever we're going from a solid to a liquid. All right, so whenever we're adding heat to a solid to a liquid, the temperature stays the same, but this latent heat is going towards, again, changing the actual structure of our material. So if we were to graph this, what might this look like? So we're going to be looking at two different materials today, water and another material called naphthalene. Okay, and what we're going to do is we're going to heat both of them up to some high temperature, around 100 degrees Celsius. So on our y-axis here, we'll have temperature in degrees Celsius. On our x-axis here, we'll have time in minutes. And what we're going to do is we're going to heat both of our substances up to the same temperature, and then we're going to turn the heat off and then let the heat dissipate. Right? And because water isn't going to undergo a phase change in this temperature range from 100 down to whatever temperature it ends up at, right? It doesn't undergo a phase change. So you'll see it constantly decreasing its temperature. So this would be water. Now, however, naphthalene is going to change its phase. Okay? It has a relatively high freezing point. All right, compared to water, which has a pretty low freezing point. So at room temperature, naphthalene is a solid. So it's going to start as a liquid, and then it's going to decrease its temperature, but at some point, it's going to start changing into a solid. And at that point, the temperature is going to level off, okay? And then after it's completely turned back into a solid, its temperature will continue to decrease as normal. So this is what our graph for the naphthalene might look like. All right, and so what we want to do is find out where is this leveling off at, and that's going to be what we call the freezing temperature of the naphthalene, and that's what we're looking for. So pretty simple second part. We're just increasing the temperature of water and naphthalene. We turn the heat off, and then just every minute we record the temperature, and wherever the naphthalene ends up leveling off, that's going to be the freezing temperature. And again, it's leveling off because instead of the heat going towards changing the temperature of the material, it's instead the molecules are rearranging into a different pattern or a different structure in the material. Okay, so that is heat transfer. Heat transfer that causes a change in temperature is the first part, and then heat transfer that causes a change of phase is going to be the second part of the lab. So we're going to go ahead and go through the procedure next. You'll see us adding hot metal to water, and then we'll go through the procedure for the naphthalene and water for the change of phase, and that'll be it for this lab. Okay, so here we have our setup for the first part of the experiment for this lab, which is going to be over heat transfer. So in here we have our two cylinders. One of these cylinders, let's take this thermometer out. One of these cylinders is going to be aluminum, and one of these cylinders is going to be the copper. Okay, and these cylinders are now in equilibrium with the boiling water that they are now sitting in. So if I want to find the initial temperature of these two cylinders, which is one of the things that I need in order to calculate their specific heat, all I need to do is take the temperature of the water. So that's what we're going to do first. All right, so if we put this thermometer in here and we wait for it to come to equilibrium, it's going to end up equalizing at the temperature of the boiling water, which is going to end up being around 100 degrees Celsius because that's the temperature that water boils. So we're not going to wait for that to completely come up to temperature, but that's how you would do that. Okay, another thing that we need is going to be the mass of the water that we have in our cup. This is going to be the water that we're going to add the metal to. Okay, and so we need, before we add the water, to take the mass of the water. So to do that, the first thing you have to do is just take the mass of the 2 cups without the water in there, which I've already done, and then to take the mass with the water and with the cups, which I've done, and then subtract the 2 so you can get just the mass of the water. So that's already been done for you, and those values are included in the table. What we also did before we placed the metal into the boiling water here, you first would have had to have taken the mass of the 2 cylinders, one for the aluminum and one for the copper, and that already has been done for you. So the only things that we need now, the only thing that we need now is going to be the final temperature of our water after we add the metal to it. So what we're going to do is we're going to use these tongs to take out one of these cylinders. Looks like we're going to do the aluminum. So we would take that aluminum cylinder out and just place it in our cup of water. And then we would take our thermometer, just stir things around, and then we're going to wait for this to come to equilibrium. So as the heat is transferred from the metal to the water, we'll see this temperature of our thermometer go up. And now we're going to have to wait a little bit because it takes a little bit of time for it to transfer all of the heat energy to the water. Right? And it means it's going to take some time for this to come to equilibrium. So you typically would wait a couple of minutes, and then we would record this temperature from this thermometer. Okay. So from all of that information, which was included in the table, you could then calculate the specific heat of the aluminum. You would do the exact same thing. We would go and dump this water out, make sure we take the mass and the temperature of the water before we add the metal, and then we would just add our copper to our cup in the same way that we added the aluminum. Okay, obviously not with the aluminum still in there. Yeah, we got to be careful not to spill stuff like I just did. All right, so that's how you would do the first part of this lab minus the spilling of the water. Right. So what we'll see doing next is the change of phase. So we'll go over there and kind of demonstrate how that part is going to work. Okay, guys. So this is going to be the setup for the last part of the change of phase for the naphthalene. So we're going to be trying to find the freezing point of the naphthalene, which is inside of this test tube here. If you want to know what the naphthalene looked like beforehand, this is it. It's like a waxy crystalline structure almost. It's the same stuff that mothballs are made out of, okay? So that's what is inside the test tube before we put it in the boiling water. And after we put it in the boiling water, it turns into a liquid. So the first thing that we're going to do in this lab is take an initial temperature at time equals 0. This glass thermometer is within the naphthalene, so this is how we'll take the temperature of the naphthalene every minute. And then to take the temperature of the water every minute, we just stick our thermometer into the water. Okay, so once we take our 2 initial temperatures, this one is about 100 degrees and the water is also about the same. This is in Celsius. Once we take those 2 initial temperatures, we're going to turn off our Bunsen burner by turning off the gas over here. So the gas is now off, and as soon as we turn off the gas, you would instantly start a timer. And then every minute we would record the temperature from the naphthalene and then from our water. And we would do this until we started to see the temperature of the naphthalene level off. So in the chart, it gives you maybe like 25 minutes. Typically, it does not take that long. It maybe takes only 20 minutes to be able to see the temperature come down and to see the naphthalene inside of this test tube go back to its solid state. Okay? So yeah, this part of the lab, very straightforward. Just turning on the heat, bringing it up to temperature, turning it off, and then recording the temperature every minute as it changes phase back from a liquid back to a solid. Okay, so that'll do it for this lab. All the data, again, is in your PDF, so you can look at the data and graph it and be able to see those graphs, and then from that, you can be able to answer all of the necessary questions. All right, so that's it, and we will see you next time.